Welcome to Spring LIB.
In this exercise, we have a spring that has a spring constant K and an unstretched length L0 that's connected to a block A that has a mass MA, which is close to a block B that has a mass MB. Now, block B is pressed against block A such that the spring is compressed by a distance D, as shown here in the figure, and then they are released. Our goal is to show that in order for block A and block B to be separated after some time, we need that D be greater than 2 times the sum of the masses of the blocks times mu K times G divided by K. And actually, I'm sorry, there shouldn't be a D here. And also, we need to find what is the distance that the blocks slide on the surface before they separate. In the formula for D, mu K is the kinetic coefficient friction. I'm sorry, kinetic friction coefficient. Okay. What we need to know in order to solve the exercise is that the elastic force F is equal to minus K times delta X. Delta X is the difference between the unstretched length of the spring and the compressed length or the stretched length. And the minus sign is to show that when the spring is compressed, the force points in the opposite direction as the compression. When the spring is stretched, the force points in the opposite direction as well. Okay, so what we need to do first is to draw the free body diagram on the blocks. So let's start by block A. Block A subject to the forces of the elastic force, F. We also have the friction force, FF. And we also have the force that block B exerts on block A, which I'm going to call N. Okay? And according to Newton's second law, we have that F minus N minus FF is equal to the mass of block A times the acceleration. Now the force, which now is the magnitude of the elastic force, is K times D minus X, where X is the distance traveled by the block. So let me draw here the spring that has an unstretched length L0. It's compressed by distance D. Okay. This is block A. Now consider that actually block A traveled a certain distance, X, after being compressed. So block A traveled this distance here. Okay. Notice that this distance is equal to D minus X, so that the force that block A experiences is equal to K times D minus X. So going back to the equation, we have K times D minus X minus N minus the frictional force, which is mu K, times the normal force that the surface exerts on the block A, and the normal force is just MAG in this situation. Okay, so this is the first equation that we obtain. And now we can carry on to block B. So for block B, we have the force N we also have the frictional force, and that is all we have. So we have that N minus FF is equal to MBG. So N minus MKMBG is equal to actually MBA, I'm sorry. Okay, so we have the two equations that I've highlighted in green. So what I'm going to do is to sum these equations, but let me first just write it here. So we have K times D minus X minus N minus mu K MAG is equal to MAB. I'm sorry, MAA. Then we have N minus mu K MBG is equal to MBA. And I'm going to sum the equations. So the n's cancel out. I get K times D minus X minus mu K G MA plus MB is equal to MA plus MB times A. So A is equal to K D minus X divided by MA plus MB minus mu kg. Okay, this is the acceleration. Now I can take this acceleration, go back to the previous equation, so this one here, for example, and find what the force N is. And I'm going to do that because when the force N is equal to 0, then the two blocks start to separate. So I have that N is equal to MB times A plus mu kg. So we have that N is equal to MB times K D minus X divided by MA plus MB. Now notice that the other two terms cancel out, since the next term would be MB, minus MB mu kg, and the other term plus MB mu kg. So we have that N is this thing here, and this is equal to 0 when D is equal to X. Okay, so the blocks need to travel a distance D before separating. Okay, so now we are in a position to calculate, to show that the inequality that the exercise gave us actually holds. So remember that the acceleration is equal to dv dt. So we have that A times V is equal to V times dv dt. And I'm going to write V as dx dt. So we have A dx dt is V dv dt. Now the dt's cancel out, so A dx is V dv. And we have to integrate it. And I'm going to integrate it from V equals 0 to V, and from x equals 0 to d. We know that the acceleration is equal to K D minus X divided by MA plus MB minus mu kg times dx from 0 to d, and this is equal to v squared over 2. Okay, so we have that k times d squared minus d squared over 2 divided by ma plus mb minus mu kgd is equal to v squared over 2. Okay, So we need the speed to be greater than 0 if the blocks are going to separate at this point D here. This is the upper limit of integration, and we know that the blocks will separate at this point. So if we want the blocks to separate, then V must be greater than 0. So we have K D squared over 2 MA plus MB must be greater than mu K GD. One of the D's cancel out. So we have D is greater than 2 mu K G MA plus MB divided by K, which concludes our exercise.